1 minute. And the administration will also know that you only attended for 2 minutes or 1 minute. So that's not a good idea. I'm trying to get my pen outside. So in the last class, I was hurrying so much because the time towards the end was so little. So I could have rushed, so I'll just do it again slowly so that everybody could follow. So this is a regulated power supply using discrete transistors, So I'll just draw the circuit. You can also take it down, please. Drawing with the computer takes a lot of time. To then move slowly. Let's assume that's our unregulated voltage. So this is a very, very common circuit in your power supplies. This is the circuit we normally use. So this is your reference voltage, so this will be your 0 volts. Normally, you can sometimes ground it for stability. So the voltage here is V0. Voltage towards the load is your V0. When you go to bias the Zener is biased from the output voltage. In the last class, we saw that Q1 is normally a power transistor connected to a heat sink. It's normally a power transistor connected to a heat sink because it's our main power dissipating device, and it's actually our control element. So the current going to the load, this one, let's call it RD. This is for biasing the Zener diode. So that Q1, the design is very critical. It should be able to handle the maximum current at the temperature. that's operating in. The power being lost through it is approximately IL times the voltage across its collector and emitter. Here, Q2 is actually our error amplifier. Q2 is actually our error amplifier. Remember the error amplifier in the earlier design. This was going to minus, and here we had beta V naught, and we had the reference like that. And this was the output was our V naught dash. So in this circuit over here, the signal coming in is your beta V naught. Our reference is our VZ. VZ is the potential across the Zener. And our output, which we are calling a V naught dash in our earlier circuit, is this output over here. So the output is here, it's your V naught dash. So here we're just using one transistor to perform the function of an error amplifier. So if you compare one transistor to an op-amp, of course it is cheap. The gain of using one transistor would be quite small compared to an op-amp, which can have a gain of 10 to the power 6 or 10 to the power 5. But a transistor is more stable because there's not a lot of feedback from the output to the input. And a single transistor is much cheaper than an op-amp. So if money is critical, then you use this circuit. I'll mention most of our lab power supplies, all our old lab power supplies, apart from those new ones that they brought, we're using this circuit. Of course, the ratio R1 and R2, and now we change it to a port. So you can slide it up or down to increase the voltage. And you can use two of them to have a positive, negative power supply. So for the bottom supply, you can use a PNP transistors. Or you can just use the same circuit, but you use two of them. So the top of one of these ones will be your zero reference. So now derive the working equation slowly. Derive the working equation slowly, so that you can all follow. Let me just mention that a long time ago, before all this color television came into play, especially LCD color televisions came to play, most of the entertainment during the day, those days, was by hi-fi equipment. So the manufacturers will make very high quality audio amplifiers, and in their power supplies, they would use this circuit over here to regulate the power supply, so that the amplifier is very silent. Nowadays, in your flat screen color televisions, what they use most of the time, it is this circuit, but with an op-amp Say that you just use those LM like the 7805, 7808, 78015. So that one makes the production much quicker, because nowadays most of the printed circuit boards are made by machines which are fed automatically. So it's faster to just put one chip than to put all these components inside a board. So that's the trend nowadays. If you open your televisions, or you open your even your laptops, and even those modern power supplies you have in the labs, they'll just have a 3-pin device which has got all of this inside. And they'll even use something, instead of using Q2 being just a single transistor, they use an integrated circuit op amp like the ones I showed you last time. Okay, so let's see how this circuit works. Last time I didn't have time to explain how this circuit works. So let's say you've designed it for voltage V0. You designed it for voltage V0, and then you increase the load. So if you increase the load, this voltage V0 will tend to drop. The voltage V0 will tend to drop. So let me just use another color to show you. So this output voltage, when you increase the load, this voltage will tend to go down. I'll show an arrow down. So it means that the divided voltage between R1 and R2, even this point, will tend to go down. The voltage tend to go down. And it means the biasing of your transistor, the base voltage will tend to go down. And for the transistor, when the base voltage goes down, the current decreases. It means the collector voltage goes up. So this collector voltage would go up. When the collector voltage goes up, it means that the drive to Q1 will increase. So the drive here will increase, and thereby try and compensate for the load, to provide extra current to supply the load. If on the other hand, the voltage was V0, and then you suddenly decrease the load, then it means that the output voltage will tend to go up. I'll use just this pin, this blue color, to show the case of less load. So when the voltage goes up, the feedback voltage beta V0 will also go up, and therefore the base drive to Q2 will also go up, and therefore the collector voltage of Q2 will go down. When the collector voltage of Q2 goes down, the base drive of Q1 will also go down. And since the emitter follows the base, less current will be supplied at the collector Q1, so it will decrease. And therefore there will be a decrease in drive current, and therefore the load will tend to remain constant. So that is how it works physically. Now let's do the analysis slowly to show what is actually happening. Let me just run this small circuit over here. So in the last class, I was rushing because the time that was remaining was quite small. So let's do it slowly. So let's analyze this circuit. and use mathematical analysis to show the behavior of this circuit. Now for this, I'll apply KVL to this part. So I'll start at VZ. So I can write VZ plus VBE Q2. So I'll call it VBE2. This is the base voltage, VBE2. This will be VBE1. So they have reached the base of Q2 plus the drop across R1. The drop across R1 will just be V0 R1 over R1 plus R2. So all this should equal to V0. So next I can write that VZ plus VBE2 can be written as V0 minus V0 R1 over R1 plus R2.
Excuse me.
Yes?
Should it be R2 R1 plus R2?
Should it be R2? No. The drop. Okay, let's go to third-year circuits. If you go to third-year circuits, if you consider current, say I, passing through due to V0, let's call this current here I. Then what is I? I will be equal to V0 over R1 plus R2. Okay? And therefore the drop across R1 will just be I into R1. But I is V0 over R1 plus R2 into R1. So this is what that is. I hope that's okay for you. Okay, so next let's solve for V0. So you'll get Vz plus VBE is equal to V0 into brackets 1 minus R1 plus R2. or the right hand side, we can simplify it as V naught. If I make R1 plus R2 my common denominator, here I get R1 plus R2 minus R1. Or V naught into R2 over R1 plus R2. Or this could have been written as V naught into beta, where beta is our feedback factor, beta is R2 over R1 plus R2. So if we call this 5, call this 6, then we have Vz plus Vbe all over beta is equal to V naught. Or we can write that Vz plus Vbe all over R2, R1 plus R2 is equal to V naught. So let's call this one 6 and this one 6b because they're the same equation. So we can see that thus from 6, V naught is a function of Vz, Vbe, and beta only. And not RL, or VI, or the input VI, which is our unregulated input. So we can say hence the circuit and the circuit functions as a voltage regulator. Because of equation 6, V naught is only dependent on Vz, V naught is dependent on VBE and beta. Of course, this is a very ideal equation. But if you're using ideal components, you got an ideal power supply with infinite current, then this equation is true. But if you're using practical components, then this might not be 100% true. Now let's see why that is not the case. The reason is number one, Vz is a function of what parameters? Iz and sometimes you use small rz and temperature. Because for most of our analysis as students, we tend to assume that as in a diode is perfect, so long as we bias it correctly, everything will be fine. But as in a diode is just a special silicon junction with an internal dynamic resistance. So if you're to model a Zener, of course, we normally draw it like this. By the top, if you're to model it, it will be like a voltage with an internal resistance. And the voltage across it is what we call Vz. And number two, beta, remember beta, in this case is R2 over R1 plus R2. But in general, R is some R0 into 1 plus alpha T. So we can say beta is a function of temperature. There are many types of resistances. The best resistances, which are most expensive, are the metal oxide resistances, where the temperature coefficient is very low. But most of the cheap resistances we find in the shop made of the carbon resistances, they were lots of the temperature coefficient is very high, and it changes a lot with temperature. As you increase it, like for carbon resistances, if you have to plot how the resistance changes with temperature, it might go something like that. This absolute temperature in Kelvin. As they get warm, the resistances become less. And then finally, the VB of the transistor is also a function of temperature. It's also a function of temperature. VB curve for semiconductors, and they're like this. If this is T2, maybe this is IB, which is proportional to IC, and this is T1. So here, T1 greater than T2. So this is your VB axis. That you should have known from your third year. So if we use equation 6, it's a very easy equation. But if you look critically at the components that constitute our regulator, you look critically at them, you find Vz will slightly vary with temperature, Vbe will slightly vary with temperature, and beta, which is a function of the resistances, will also slightly vary with temperature. And of course, you should remember that practical resistances cannot be made exact. Okay, they're always made with a tolerance. So you can buy resistances with plus minus 5%. This will have the gold band at the end. You'll have some resistances with manufactured to a tolerance of plus minus 10%. That will have a silver band at the end. And then you have resistances with tolerance greater than 10%. Those ones will have nothing. Yeah, from your first year, I hope you studied resistances, the color coding of resistances in your first year. This is a resistor. You have the first color, the second color, which is the second digit, third color, which is your multiplier, and the fourth color is your tolerance. So this will define whether it's 5%, 10%, or greater than 10%. So if this is like red, say red, yellow, and this one is gold. And what's this resistor? This will be 2, 2. Yellow is how much? Yellow is 4, isn't it? Orange is 3. I think so. I'm just guessing that one. Plus minus 5%. Anyway, that's not necessary for you. You're in 5th year. Unless you've forgotten what you were taught. Okay, so now having this knowledge that the output of our regulator is a function of all these other parameters. So please take down, because I'll just put an equation over here. Please take down, and you're using your pen. So knowing that the output of the voltage regulator is a function of these parameters, we characterize A regulator with what is known as the stabilization. We characterize the regulator with what is known as the stabilization, which is how the output changes, which is how the output changes which is how the output changes with respect to the input voltage, the load current, and the temperature of the regulator. So you can characterize the performance of a regulator with a factor known as the stabilization, which tells us how the output varies as a function of the input voltage or variations of the input voltage. Equation, and write this equation here. The change in the output voltage, which we normally call delta V naught, can be written as change of V naught with respect to change of Vi into small change Vi plus change of V naught with respect to change of IL into delta IL plus change of output voltage over change of temperature into delta T. Or in short, we can write that delta V naught is written as SV into delta Vi plus SL. Let's confirm this second variable here, and then we give it the units of delta V naught over delta IL. We normally call it R naught. Into delta IL, and this one we call it ST into delta T. can say where the three coefficients are defined as follows. The input regulation factor which is called SV is equal to delta V naught over delta VI when delta L delta T is equal to 0. And then the output resistance, the regulator, we normally call R naught, is given by delta V naught over delta IL when delta V naught is equal to 0 and delta T is equal to 0. And the last one is the temperature coefficient, coefficient 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 is called ST, which is defined as delta V naught over delta T, where delta V naught is equal to 0 and delta IL is equal to 0. So you take down that. I'll give you a minute for it to sink in, and then we'll conclude. So in summary, we can write the smaller the values of the three coefficients, the better the regulation of the power supply. So for a practical regulator, we want this variation with respect to input voltage, respect to load, respect to temperature to be as small as possible. So the smaller these coefficients are, the better the regulator. Next, let's say note that delta VI means this changes in the input may be due to change in supply voltage or ripple due to inadequate filtering. due to inadequate filtering. So if you had to look at the circuit of the typical power supply, I'll just draw it in terms of a small block diagram over here. So like the lab power supply, so most of the power supplies, you get 240 mains coming in. Now, if the voltages you want are lower, then you normally use a step-down transformer. And then you pass it through. You pass it through. Through a bridge rectifier. So over here, when you rectify, if it's a full wave rectifier like this one, they will get varying DC. Then you use smoothing capacitors. So this is what we call filtering. Depends on the value. So this will store the charge until the next ripple comes in. But a small current will be flowing through the capacitances, called the ripple current. The larger the capacitance, the better. What's the more expensive your regulator? That's when you put your regulator. And that's when you connect it to your load. So if Kenya Power, so let's assume, me I've never seen 240 where I stay, it's normally around 230 volts. So if the input is 230, and then the output was say 40 volts, say, and then the input increases maybe to 240 here, and the output will increase with the ratio of 40 times 240 over 30 will be your AC voltage, because here the 40 volts is still AC, and that is rectified and smoothened with capacitors. Now let's do this final problem, and we call it a D. I gave you some other problem. Let's do this final problem. So any questions on this so far? Now, for those of you who want to see what happens at the end of the class, wait, do not log out. I'll show you how the computer takes attendance automatically and record how long you've been in the class. So let's do this simple problem. If you can do this, you'll get 10 out of 10 for this question. Let me see. Let me save it in Save As. Let's call it regulator. And today is December 9th, 2024. Okay. Oh, it's still saving. Okay. Excuse me. Okay, get your pens ready. This is R naught. It's 10 ohms. This is the resistance of your power supply. Looking back, and this is your input VI. This is your series element. So they're using 2N1722. This is 13. 50 ohms. This was our R3. Here they're using 2 Zenas. And these Zenas are IN755. This is 1K. And you're told that IL is 1 amp going to your RL. So this is your RL. So this is V naught. This transistor is 2N930. So you're given the data for 2N1772. It's a silicon transistor. So for the 2N, I'll put here data. For the 2N1722, given the data that H capital FE is equal to 125. And H small FE is equal to 100. And HIE, the same transistor, is 20 ohms. Now for the Zenas, the IN755, this one, the data is that VZ is 7.5 volts. And RZ is equal to 12 ohms at 12 milliamps. And for the 2N930, for the 2N930, I'm sorry, I think there's been a problem with my network that I normally use. I don't know why it always has this problem towards the end. So now I've changed my network to a slower network, so the response might not be very fast. Sierra, please tell me if you can hear me. Sierra.
Yes, we can.
Okay, I'm trying to put back the presentation. I'm in a very slow network. I'm trying to see how I can speed up this network. Okay, let's just stick with it. When I write, it will appear very slowly on your side. So let's continue. We are getting the data for the 2N 930. 2N 930. We saw IC max for this one. You are given is 30 milliamperes, and VCE max you're told is 45 volts. And then you're told that H capital FE for this transistor is 220, and H small FE is 200, and HIE2 means that this is actually our Q1, the top one, and this is your Q2, is 800 ohms. So all these parameters, you're told it's at IC is equal to 10 milliamps. So the question is, with the input voltage, you're told varies, input voltage, I just drawing the diagram, varies from 50 plus minus 5 volts. VI is 50 plus minus 5 volts. So you're told to find the following. Let me put it back here. You're told to find the following. Oh, wait. R1 and R2 have not given you. R1 is 930. And R2 is 1570. So this is your R1. This is your R2. So you're told to find out. So problem is, number one, find the output voltage. Problem number one is find the output voltage. When the input voltage is 50 plus 5 volts, and when the input voltage is 50 minus 5 volts. Hence, find the stability factor SV. Hence, find the stability factor SV. So question 2 or part 2. Find the current through R3. Find the current through R3. At the prescribed output voltage. The current through the base of Q1. The current through the collector of Q2. The current through the Zener diodes. The current through the 1K resistor. And the currents through R1 and R2. When the load current is 1 amp. When the load current is 1 amp. I didn't write this load current properly. This is a load current. So if you can do this, you'll get 100 out of 100 for the equations of series regulators. I hope everybody has taken down the parameters that are there in the circuit. I said this is a very common circuit in audio high-powered amplifiers. For high-powered amplifiers, like the ones for PA, and the ones which are about maybe ranging from 1,000 watts to 5,000 watts RMS output, Q1, you use many of them in parallel. And even the driver transistors, it will be actually a Darlington now. It won't just be one transistor. It will be driven with a Darlington. Okay, if you've taken this, then we can go to some exam papers. Anybody who's not taken, just switch on your mic and say, I have not finished taking the data. Okay, everybody has taken. Let's save this one in case I send it to your Google Classroom. Regulator exercise. Last year's exam, but that is not, doesn't have hours. Where is the exam again? FEB syllabus. I don't have any exams here. Okay, maybe it was award. Let me see. And I normally put them in the exam folder. Let me see. It should be inside an exam folder somewhere, starting with the E. Let's see these exams. The folder is empty. Some people have hacked me. Somebody must have hacked me. What's even documents? Okay, let's go to my desktop. Exam draft. Okay, let's see 2022. What is here? This is second year. Let's see this one of 2023. That's third years. Okay, let's see supplementaries. Instrumentation. Okay, there's one here. Supplementary exam. Okay. Let me decrease this. So you got to know how to do this. So this is a question on, everybody panics when I start a question like this. Everybody panics, like this one on multipliers. I said this one on multipliers. I don't know why everybody panics. Okay. So like this question, let's decrease this one a bit so that it fits. So question 2, compare the quarter square technique versus that. This is just easy marks. Okay, then you're given this. So this is an IC-based multiplier. Of course, everything is not complete, but I tell the students where to connect all this pin number 2, pin number 14. Like you can see this Q5, Q6, Q7. These are all Gilbert's multiplier. And then when I ask you to find the currents, nobody's able to answer the quiescent current. So like this one, I've told you that pin number 1 is connected to positive VCC, which is 15 volts. Pin number 2 and pin number 14 are connected via a 3K to positive 15. What is this? Pin number 2 and 14. Yeah, because this one should go to the load. Okay, there's supposed to be a 3K resistor to the load. Then I tell you how to connect all these pins. All the students, they ignore. In fact, some of them start answering their own questions. They modify this question to answer the question, to answer the question on the very basic Gilbert multiplier side, which we start with, which we say is approximate. So it's only the brave students that do that. So I've shown you how to connect the pins. And if you look at the data sheet of the MCU 1496, you'll find the same thing there. And there's an application circuit which the manufacturer tells you how to use it, how to connect the voltage, which pin to connect the voltage, how to connect external resistances. Okay, but we are doing, so this is the topic we're doing now, list the salient features of series and switch mode regulators, hence state which applications they're best suited. Then you're told the regulator of figure 3 is required to supply nominal current of 4 amps from the input, from an input that varies from 15 to 40. So like this problem I've given you, the output voltage varies from 50 minus 5 to 50 plus 5. So you're told to evaluate the output voltage given that the op-amp has got a loop gain of 100,000 and the transistor BB says that. So the circuit is very simple. This is just bread and butter, which I will not set to you people this time. This is bread and butter, and you people don't want to do it. Only about half the class gets it right. Yes, a 1 minute 1 minute and you get about 5 marks. Because you're dealing with the ideal pump, ideal transistor, etc. Then you're told that given that Q1 has a gain of 400, design the requirements of Q1 if the op-amp has a maximum output, drive capability of 10 milliamps. So you're told the op-amp can only give a maximum of 10 milliamps. But in your design, you're supposed to design it for, I think it's part 1 of the equation, which I think is 4,000 amps, or 4 amps, yeah. 4,000 amps. So 10 milliamps coming in. So you got 10 milliamps, maximum outs here. And the load current you're supposed to supply is 4,000 milliamps. But you're told Q1 has got a HFE of 400. So just as a rough test, milliamps times 400 is already 4,000. So everything is okay. Then you are told to calculate the dissipation requirements of the Zener transistor. Calculate the dissipation requirement of Zener and transistor. So power dissipation of Zener, let's start with that one, is easy. Power dissipation of transistor, of Zener is just IZ into VZ. And what is IZ? IZ, you use maximum input because you're told the maximum input varies from 15 to 40. Okay, you're told the maximum input varies from 15 to 40. So this input here is from 15 to 40 volts. So you go to design it for the worst case when you have maximum voltage. And therefore, you get the maximum current through the Zener. So the maximum current will just be 40 minus 5.1 divided by 1K milliamps. And therefore, the power is just 5.1 times that current. And what is the last one? Dissipation of the transistor. Dissipation of the transistor. You go to first of all get the load voltage, if you not. So the dissipation, maximum dissipation will be maximum voltage at the input, which is 40, minus V naught, will give you the maximum voltage across the transistor, times the maximum current that is going to pass through, times 4 amps. So it's just bread and butter. But I don't know what happens to you guys. You make us set supplementaries. Okay, now this is a type of question for your switching power supplies. You can go and do it for the switching power supplies. Question 4. And that's a question for the switching power supply. So go and check this year supplementary. This was connected this year supplementary. You should know how the switching power supply works, how it works. You're able to design a switching power supply. And that is it. It's so simple. So I'll stop about there. This is now your assignment. That topic, I told you the book I use is Professor Sen, Power Electronics by Professor Sen for this area. Okay, so let's stop over there, but don't log out. Don't log out. I'll show you the presentation of the automatic attendance system. Don't log out. Let me close this. I'll log out because that thing only works after I've closed the class. But you people don't log out. Then I'll try and join the class and show you.